Swayam Prabha. Digital India. Educated India.
Now, how many equations does each of these things give us? Of course, it depends on the circuit itself, the configuration of the circuit, but if we have n nodes and b branches, these n nodes will give you n minus 1 Kirchhoff's current law equations. Okay. Let us consider the same circuit again. I will illustrate it with this example, but this is true of every circuit with n nodes. Okay. So, we have nodes 1, 2 and 3 and branches 1, 2, 3, 4, 5, 6, 7, 8. Okay. We also have node 4 over here. Now, I will just label the currents in each branch in some arbitrary direction, it does not matter, I 1, I 2, I 6, I 3, I 4, I 5, I 7, I 8. Okay. Now, we can write Kirchhoff's current law equations at node 1. What do we have? The sum of I 1, I 2, I 6 and I 8 to be 0. Okay. In fact, I would encourage you to pause the video at this point and then write the KCL equations at every node by yourselves and then restart the video and verify that whatever you have got is correct. This is just to get some additional practice in keeping all the signs in the KCL equations correct. Okay. So, at node 1 we will have I 1 plus I 2 plus I 6 plus I 8 to be 0. At node 2, I will again have the sum of currents leaving the node to be 0, which is I 3 minus I 6 plus I 7 equals 0. Node 3, I 4 plus I 5 minus I 7 minus I 8 to be 0, and finally, at node 4, we will take the sum of currents leaving the node, which is minus I 1, minus I 2, minus I 3, minus I 4, minus I 5 to be 0. So, it looks like at every node we can write a KCL equation, but in this case let me consider the sum of these three equations. Okay. I sum these three equations, what will I get? You can see that I 6 will cancel with minus I 6, I 7 will cancel with minus I 7 and I 8 will cancel with minus I 8, and I will have all these other things which are left out, I 1, I 2, I 3, I 4, I 5. So, if I sum all these equations, I will get I 1 plus I 2 plus I 3 plus I 4 plus I 5 to be 0. And you notice that this is exactly the same as the equation for node 4, but with the signs reversed. Okay. So, basically the fourth equation is dependent on the first three equations. We have only three independent equations. So, in general, in a circuit with n nodes, we will have only n minus 1 independent Kirchhoff's current law equations. Okay. Now, this is not a particular property of this circuit. This is not a property of this particular circuit, but true for all circuits. Okay. I will quickly show why that is the case. Let me copy over this circuit. Now, let us consider a particular node, for instance, node 4. Okay. So, I will draw a surface enclosing node 4. Okay. Now, let me also draw a surface enclosing all the other 3 nodes. Okay. So, this one is a surface enclosing 3 nodes 1, 2 and 3. Okay. So, in general, if you have an n node circuit, you imagine a surface enclosing n minus 1 nodes. Okay. And this one here is a surface enclosing the remaining one node. Okay. Now, let us write KCL equations. If we do that, what we will be writing is the total current leaving this node. Okay. In this case, the KCL equation for the last node, KCL equation, what this gives you is sum of currents leaving this node. Okay. Now, clearly, one of these surfaces encloses n minus 1 nodes, the other surface encloses the remaining node. So, the sum of currents leaving this node is exactly the same as the sum of currents entering the other surface. Okay. The sum of currents leaving this green surface here is obviously equal to the sum of currents entering the blue surface, because blue surface encloses the rest of the circuit. Okay. So, this also equals sum of currents entering this surface. Okay. Now, when we write Kirchhoff's current law for the first n minus 1 nodes, what are we really doing? We are taking the sum of all currents leaving this node and all currents leaving that node and all currents leaving that node and so on. And if you sum all of those equations together, what we get is exactly the sum of all currents leaving this blue surface. Okay. So, let us consider the n minus 1 KCL equations. Then the sum of these equations is basically the sum of currents leaving this surface. By this I mean the blue one. Okay. So, that is because the n minus 1 KCL equations will have currents going between nodes inside the same surface. Those will get cancelled out, because when you write it for node 1, it will appear with one sign. When you write it for node 2, it will appear with another sign. So, when you sum all the equations, the only things that will be left are the actual currents going out of this surface. Okay. So, now you clearly see that the KCL equation for the last node, which denotes the currents leaving the green surface and entering the blue surface, is obviously the exact opposite of the sum of the first n minus 1 KCL equations, which denotes the sum of all currents leaving the blue surface. Okay. So, there are n minus 1 KCL equations. I hope that is convincing.